Good morning. I will state the Kirchhoff circuit laws. First of all, the current law. The algebraic sum of the currents flowing into any node of circuit is zero. Is the sum of all the algebraic sum of the currents at this node, this node, this node, and this node are zero. Voltage law. The algebraic sum of the individual potential differences across each circuit element in a loop or a mesh of the circuit is equal to the algebraic sum of the EMFs acting in that loop or mesh. As an example of the application of Kirchhoff's law, we are going to consider analysis of the bridge network shown here. So on applying the current law, we obtain at node A we can write at node A we can write that I minus I2 minus I3 is equal to 0. Those that enter are positive and thus that are out of the node are negative. At node B, we can say that I2 minus I4 minus I6 is equal to 0. At node C, we can say that I3 plus I4 minus I5 is equal to 0. Now, on applying the voltage law for mesh X, A, B, D, Y, X, for example, for mesh X, A, B, D, Y, X, we can write that V, if we have chosen the direction of the current, so it means that the voltage drops in this resistance, on this resistors, are this way. So VR1, VR2, VR6. So if we start from X going in this direction, clockwise direction, if we go this way, we can say that minus VR1 minus VR2 minus VR6, and here we're coming out of from minus to plus, so we write plus V is equal to 0. Here we go from plus to minus, so it means its sign we take minus. Let's write now for mesh ACBA. ACBA. Here we have chosen currents this way, so VR2 is like this. So this one will show us the most positive potential. Here the current flowing this way, so this is VR3, and the current is flowing this, the voltage drop is this way, this is VR4. So if we go clockwise, this will be plus VR2. Here we're going from plus to minus, we write minus VR3, and here we're going from minus to plus, we write plus VR4. and it's equal to 0. Now for mesh BCDB, we can show VR5 is in this direction. So if we go from this point, we can write, because we are going from minus to plus, we write plus VR6. Here from plus minus VR4, and here we're going from plus to minus, so we write minus VR5, which is equal to 0. You see, we have 6 equations which we may solve for 6 unknowns, unknown currents, I1, I2, I3, I4 and I5. But here I'm going to use something different to solve this problem. I will do a transformation, delta star transformation, and later I will calculate the equivalent resistance, and then we can calculate the main current, and from there we can calculate all the currents. Let's do the transformation. R4 prime is equal, R4 prime is R2 R3 over the sum of the 3 resistances, and R2 prime is R3 R4 over the sum of these resistors, and R3 prime is equal to R2 times R4 over the sum of the R's. So it means, did I calculate it somewhere? So R2 prime is 120. You can do it yourself. I will give you the results. R2 prime is 120. R3 prime is 60. And here we have 80 ohms. Okay, so we will now come to the new circuit, which we will have. Here I will draw it. Now we have a circuit that looks like this. R4 prime, R1, R3 prime, R2 prime, R6, and R5. This is the source voltage. Here I, here I6, and here I5. So let's calculate the equivalent resistance. These are in series, R3 prime plus R6, that are in parallel with R2 prime plus R5, and the whole of these are in series with R1 plus R4 prime. So we can now start calculating the equivalent impedance, resistance. Here it's 60 plus 150 ohms, so it gives us 210 ohms, in parallel with, here we have 120 plus 160 That will give us 280, and we can calculate this. That gives us 120 plus R1, which is 50, plus R4 prime, which is 80. That will give us a value of 250 ohms. From here we can calculate the main current I is equal to V over RE, equal 250 over 250, it's 1 amp. From here, current divider, we can calculate I6 and we can calculate I5, current divider. So I6, it's this 2 over the sum of the 4. Times the main current. Here it's R3 prime plus R6 over the sum of the 4. R2 prime plus R5 plus R3 prime plus R6 times I. And this will give us 280 over 490 times 1, and here it's 210 divided by 490 times 1 will give us 0.428, and here 0.572 amps. Okay, now that we have calculated the current I6, we are going to calculate now I2, here is R2, I2, here it's R4, Y4, and here we have R3, and we're going to calculate I3. So let's start by calculating the I2 by calculating the drops here, the voltage drop VR6. Let's change this one. VR6, it's R6 times I6, it's R6 is 150 times 0.572, and it's equal to 150 times 0.572, 85.8 volts. VR1 is equal to R1 times I. It's 50 times 1, it's 50 volts. So it means that V is equal to, or we are going to calculate VR2. It's V minus VR6 minus VR1, and it's 250 minus 85 plus 50, 135.8, and this is 114.2 volts. From here we can calculate I2. It's VR2 over R2. It's 114.2 over R2, which is 180 divided by 180. It's 0.634 amps. And I3 we can calculate it because at this node I minus I2, it's minus or plus 1, and it's 0.366 amps. We have calculated I2, I3, and we are left with I4. I4 is I2 minus I6. I2 is 0.634 minus I6, 0.572, and the result is 0.634 minus 0.572. It's equal to 0.062 amps. And that's it. We have calculated I2, I3, I4, I5 and I6. And that's it. Thank you very much.